In this video, I introduce mixture density networks for prediction improvements. A new network directly predicts the conditional probability P of a target T given an input X. Suppose that the density P is Gaussian distributed. A density network predicts the conditional probability P by computing the mean and the deviation of the Gaussian distribution, where the mean and the deviation indicates the location of the output and the possible deviation of the output from the target respectively. The density network is trained by minimizing the least squares error as shown here and explained in this figure, this input, this hidden layer, and this output. Where Fk is output of the density neural network, XQ, DQ is the training dataset, and W is a model width. The minimum E is obtained at W asterisk. The variation sigma square of a B distribution is computed by using this equation. A mixture density network consists of a feed-forward neural network and a mixture model, as shown here. Is feed-forward neural network and this mixture model, which represents the conditional probability density P as a linear combination of kernel functions as shown here, as phi and this alpha, where M is number of components in the mixture. Alpha I is the mixing coefficients generated from the component I in the mixture. And phi I is the conditional density of the target T for the kernel I, which is sampled from a Gaussian distribution with a mean mu I and variance sigma I as shown here. The components of output T are statistically independent with each of the distribution. If the mixing coefficients mean and the variance are correctly selected, the Gaussian mixture model can approximate any complex density function. The feed-forward network takes X as an input to output Z, and the mixture model uses Z to generate alpha, mu, and sigma, which are combined to approximate the conditional probability density P, as shown here. This input, this neural network model, this output, and this is the mixture model, and this is the final output. A regular neural network generates C outputs Tj, number of labels give input X. However, the feed-forward neural network in MDN produces C plus T by M outputs Zg as shown here. The kernel function phi I is sampled from mu I and sigma I. The conditional probability P is computed by the mixture model using the coefficient alpha I and the kernel function phi I. The kernel coefficient alpha I, prediction deviation sigma I, and the location mean mu I are computed from the corresponding outputs Z as shown here. The error function is defined as a negative logarithm of likelihood E, where E Q is the contribution to the error from the pattern Q as shown here. To use backpropagation to train the mixture model, we need to compute the derivatives of error function EQ with respect to alpha, sigma, and mu as shown here. This pi I is computed from this normal formulation. The regular backpropagation goes through the neural network. For more details, please check with these references. Thank you. Bye.